Hello students, today we'll be looking at Chem 233, Organic Chemistry 1. In level 100, we saw that certain atoms can form bonds with each other and other atoms. So we call this catenation. And a classical example was carbon atoms. So we saw carbon atoms having the ability to what? Catenate. So before we proceed, let's do some basic revision. We need some basic concepts from level 100 so we can survive this course. So let's establish this fact. Carbon can form a maximum of 4 bonds. Oxygen can form a maximum of 2. Sulfur can form 2. Nitrogen can form 3. Hydrogen can form 1. These are the number of bonds that these atoms can form. And all these bonds, we call them what? Covalent bonds. Covalent bonds. Why covalent bonds? Because there was sharing, it was electrons. So here electrons have been sharing. You bring one, I bring one, we put it together, that's 2 electrons. We form a bond. Then we represent it, that bond by a dash. So that is organic chemistry for you. All right. So now that we know this, we should also know the halogens. We'll be meeting them here. The halogens are what? Simply group 7 elements. You can go back and watch my video on the periodic table. You will come across the halogens: fluorine, chlorine, bromine, iodine, and astatine. FC Barcelona in Accra. But basically, we'll be meeting these, the first four: fluorine, chlorine, bromine, and iodine. Astatine is another level. All right. So what how did we represent bonds in what? In level back in level 100. We said that was we have a plane. Now in the plane there some bonds will be pointing towards you, some bonds will be pointing away from you, and some bonds will just remain in the plane. So we call this solid wedge, broken wedge, and what? And just in a straight line. So we already know the solid wedge. Something like this. So this is our solid wedge, and this is going to be our broken wedge. And this is just going to be our straight line. So the solid wedge is what? The bond that is pointing towards you, or we say it is pointing out of the plane. But this one, broken wedge, is a bond that is pointing away from you. You are the observer, so it's pointing away from you, or it is pointing where? Behind the plane. And the straight line, we said that was it is in the plane. So we have the straight line in the plane, this one behind the plane or away from the observer. We said this one out of the plane or towards the observer. Someone can also say out of the page. It's the same thing. Okay, so now we met some functional groups. We met alkanes. Alkanes, in some situations they are functional groups, in some situations they are not. So if something is not always true, then it's false. So we have alkanes, we have alkenes, we have alkynes, the alkanols are there, the ethers are there. All right, bound to establish something. Um, we have sp3 hybridization, sp2, and sp. So that's what I want to establish now. So what did we say about this hybridization? We said if an atom has 4 different groups attached, then its shape is going to be what? Tetrahedral. So you have an atom A, which has 4 different groups attached. This is going to be what? Tetrahedral. If it has um, just 3 different groups, it's going to be what? Trigonal planar. And if it has just, let's say, 2 groups, it's going to be what? Linear. I don't even think I represented this in this wall because the linear should be something like this. Yeah. And the trigonal planar should also look better than this. And so we saw that alkanes were tetrahedral, they had four different groups attached, and the bond angle here was 109.5 degrees. For trigonal planar, the bond angle was 120 degrees, and for linear, the bond angle was 180 degrees. And we saw the various types of hybridization in all of them. So alkenes have sp3 hybridization, alkenes do have sp2 hybridization, and alkynes have sp hybridization. Tetrahedral, trigonal planar, and linear. And the bond angles 109.5 degrees, 120 degrees, and 180 degrees. All right, we had a general formula for alkenes, and that general formula was CnH2n plus 2. And we said N is the number of carbons. How many carbons can you see? And this is this word, the alk here means how many carbons can you see? Number of carbon atoms. And that's represented by N here. So we said if it's 1, we call it met. If it's 2, et. 3, prop. 4, but. The rest we use polygons. If it's 5, pent, as in a five-sided polygon is pentagon, pentagon, hexagon, heptagon, octagon, nonagon, decagon. Yeah. So from build to go to pent, hex, hept, oct, and so on. I'll do a whole video on naming, so we'll talk about this later. All right. So if let's say I have C for H, 2 times 4 is 8 plus 2, 10. So this is going to be what? Butane. So how do I represent this? So four carbon atoms bonded to each other. Then we said carbon can form four bonds, a maximum of four bonds. The equivalency is here. Equivalency is the number of bonds the atom can form. So for carbon, as we arrange it this way, we can add three more here, and here is going to be our hydrogens. So this one to take hydrogen, hydrogen. This takes hydrogen, hydrogen. This takes hydrogen, hydrogen. Just follow what we are doing. You get me. We are going to apply every single thing I'm saying here in your Chem 233. Just in case you forgot, and that's why I'm doing this revision. Good. We are not going to be seeing it like this. We are going to be seeing the straight line, the broken wedge, the solid wedge. So we'll transform this to that very soon. So now I want you to make a careful observation. Look at the carbon at the ends, this carbon and this carbon. What can you see? Yes, the carbons at the ends have what? Three hydrogens attached. Three hydrogens attached. You see? And the ones in the middle have two hydrogens attached. This is because we want to satisfy the equivalency. This one has how many bonds? One, two, three, and four. The fourth bond is attached to another carbon. This one too has how many bonds? One, two, three, and four. So all of them equivalency is satisfied. This hydrogen is having one bond. This one bond. This one bond. And we establish the fact over here already. All right. So now that we know this, instead of doing this, we are going to do it like this. A point is a carbon. So this is my first carbon, my second carbon, my third carbon, my fourth carbon. And this is what? My butane. From this to that. Now take note. Here the hydrogens are invisible. So if we at the end here, you know that the end carbon should have three hydrogens. So you know there's three hydrogens bonded here. There's two hydrogens bonded here. Two hydrogens bonded here. Three hydrogens bonded here. Now that is what you have to keep in mind. Never forget that. All right. Then we said that if this alkene loses one hydrogen, it's going to form an alkyl group. So CnH2, and instead of plus 2, make it plus 1 because it has lost one what? Hydrogen. So C4H9. This is going to be what? Butyl, because we call this alkyl group. Alk is the number of carbon. How many carbons? 4. So but, that's the alk, and add the YL. So butyl. Like here, we saw 4 carbons. Alkane. So the alk is but, we add our ane. So butane. Just like that. So our groups, alkyl groups, representing them by R. So this will help us get other functional groups. So this is what? The alkanol, and then this is what? The ether. Later on, we'll talk about their naming and everything. I just want to give an overview. So let's look at how some reactions take place in organic chemistry. ionic reactions and radical reactions. Just a little bit about their mechanisms. All right, so bonds can be broken in two forms in organic chemistry. We call it cleavage. If you break a bond, we call it cleavage. You have cleaved the bond. So we have homolytic cleavage and heterolytic cleavage. So let's look at the first one, heterolytic cleavage. So you have AB. They form a bond. How do they form a bond? So let's represent it carefully. A dash B. So this dash is what? The straight line. This is the bond. How did they form the bond? A brought one electron, B brought one electron, and then they entered into a covalent bond. They got married. So you brought one, we have a bond. So now we are going to break this bond heterolytically. What does heterolytic mean? Hetero means unequal, right? So you formed the bond, you brought one, but now we can see that um, only B is taking all the what? Electrons. So this is called a full arrow. Full arrow means you've taken all the electrons. As you're breaking the bond, you're giving all the electrons to what? Atom B. So this is what it's going to give us. Since if you take all, A will not have enough electrons again. So if you are deficient in electrons, then you are positive. But if you have excess of electrons, B took his eighth electron in addition to eight electrons, so it's now having excess. If you're having excess, you'll be what? Negatively charged. So heterolytic fission will give us what? Ions, positive and negative ions. Then now we have homolytic cleavage. Yeah, cleavage or fission. Yeah, we are breaking the bond. Now we want to break the bond homolytically. So the same A and B, we know what is here. A brought one electron, B brought one electron, they form the bond. We can see it here. So here, B takes half, so half arrow, and A also takes half. So I'm using half arrow here, meaning they share this what? Equally. Homo means what? Equal. So we have what? A is taking what he brought, B is also taking what she brought. So here they've divorced and then they share the properties equally. No cheating. So this is what homolytic what cleavage. And these ones we don't call them ions anymore. We call them what? Radicals. In fact, free radicals. Good. So we should take note of this. We are going to apply it. Very soon we'll go to your friend is saying. We'll go to alkenes, we'll go to mechanicals, we'll anti-mechanicals, we'll be applying all these things there. So just follow everything I'm doing. Now, how do we get these free radicals? This one, we need sunlight or UV light, so we can generate these free radicals. So in your homes, if your gas is leaking and you enter the room and you detect the smell of gas, you don't on the your light bulb at once. You go and maybe turn it off, fix the problem before later on open the windows for the scent to go, the gas to move out before you on the light. If you on the light, that source of light is going to what? Cause reactions to occur, free radical reaction to occur, free radicals to be produced, and then your house will explode because these free radicals are very, very reactive, and we'll see them very soon. So let's take methane, CH4. Why am I saying methane? Because I see one carbon. If you compare to the formula, it is an alkane. If you put one here, 2 1 2 plus 2 4, so methane, and we react it with chlorine, what will happen? We can't just proceed. We have to look at the procedure. So first of all, chlorine, we need light or sunlight or UV light to separate it into chlorine radicals. We know how this is going to happen. So Cl2, meaning Cl bonded to another Cl. This takes half, this takes half. Homolytic cleavage. And we got this. Our CH4, CH3, we can show a bond with the fourth hydrogen here. We can represent this, we can represent that. We can also get something like this, homolytic cleavage. So these two can now marry. We bring one, I bring one, we marry. Hope you understand the mechanism now. Bring one electron, they can also what? Marry, HCl. And this can continue a series of steps, but I just want to revise you on this. This is just something, a basic revision. All right, so now let's look at selectivity of the halogens. So fluorine, chlorine, and bromine and iodine, we are going to use them in the lab. They are going to undergo these free radical reactions. But which ones do we use? I'm just talking about this free radical reaction I just illustrated here. So we should know that fluorine is very, very, very reactive, very harsh. So it can cause a lot of problems in the lab. So we don't normally use it in the lab. This is somehow better. This is also better. And this is very, very slow to react. So we prefer to use chlorine and bromine in this case. So now we should also know, now we've sieved out that we are using chlorine and bromine. Now bromine is what? Very, very, very selective. Bromine would like to go to where there is stability. Now let's talk about stability. If you have a carbon atom bonded to only one other carbon atom, then this is going to be what? A primary what? Carbon. If you have a carbon atom bonded to two other carbons, it's going to be a secondary carbon. If you have a carbon atom bonded to three other carbon atoms, this is going to be a tertiary carbon. Now, who is stable? So consider this. This is somebody in primary school. This is somebody in, let's say, SHS. This is somebody in uni. So as you compare, the one who is in a higher level is more stable. So the tertiary carbon is more stable than the secondary carbon, which is also more stable than the primary carbon. Now, since bromine is more selective, if bromine is going anywhere, bromine will be looking for somebody who is what? Tertiary. If you have only secondary and primary, bromine will go to the secondary. If you have primary and tertiary, bromine will go to the tertiary. If you have secondary and tertiary, bromine will go to tertiary. But for chlorine, it can go anywhere at all. Chlorine will go for all of them. Just take note of that. All right, so the last thing I'm going to talk about is going to be the Canning-God Prelog system of naming. So over here, you have to identify a carbon that has four different groups attached to it. Then we are going to call it a stereo center or a stereogenic center or carbon. So if you look here, this carbon we said has what? Three hydrogens attached. It's at the end and bonded to this second carbon. So already there are three hydrogens here. They are all hydrogens, they are not different. We want a carbon with four different groups. You check here, one hydrogen, carbon, carbon, no, no. There are already two things in common. We come here, hydrogen CH3, two bonds. The third bond is C with two hydrogens, and then C here with three hydrogens. So all here is different from all here because we can see C with two hydrogens and OH. So this is our carbon with four different groups bonded. So what do? We are going to assign priorities. So if you have the greatest or highest atomic number, we'll give you 1, followed by 2, 3, and 4. So if you have the least atomic number, then you are going to take number 4. So over here, this is what we have. Good. You can see hydrogen. Here is a carbon with hydrogens, carbon, carbon. So we look at the atoms that are directly attached to this carbon. So directly attached, you can see a carbon here, hydrogen here, carbon here, carbon here. So hydrogen is the least here. So to take number 4. Then now we move carbon, carbon, carbon. The next three directly attached are all carbons. So what do you do? When you encounter this, you are going to what? Break ties. You are going to break tie breaker. So this is what you do. If you take this carbon, what are the atoms bonded to it? It's just hydrogens. Okay. So it's just hydrogens. So only hydrogen. If you take, so this is for the CH3. If you take this carbon, what is bonded to it? We have two hydrogens here and then OH. So what are the different atoms here? The second, so let me, the second part here, we have carbon with two hydrogens, CH2, then we have OH. Hope you remember, we established this fact already, that the carbons in the middle will take two hydrogens. Yeah. So it's having OH2. So what are the different atoms here? Aside the carbon, we have hydrogens and oxygens. So we arrange them in from biggest to smallest like this. Then here we can see carbon with two hydrogens, another carbon here with three hydrogens. Sorry, here's two. So what do you do? Aside this carbon, what other atoms? Carbon and hydrogens. We arrange them from biggest to smallest in terms of atomic number. So right now, we now break the tie. We've arranged all of them in descending order of atomic number. So hydrogen, oxygen, carbon. Who will win over here? We are comparing. So you can go back and watch my video on the periodic table. We know that who is the highest here. Yeah, oxygen is the highest because hello, hello, listen, BBC News on Friday night. We came to carbon before even going to oxygen. So oxygen is greater here. So this side is going to be my number one, followed by we are left with this and this. Comparing, we are still on the first thing. This guy win. So this is my number two. Then obviously this is my number three. So we are done. When we are done, ignore the number four and then what? Trace the numbers one, two, and three. So if you trace it, we are going what? This way. That's clockwise, right? Good. But there are a lot of rules governing this. I'm going this way because my list number, which is four, is on the broken wedge, so I'm free to go this way. But I'll do a whole video on um, counting God pre-log system and give you all the rules. There's no always you can go like this. Most of the times you have to do. Sometimes you have to do rotations. But if you are always doing rotations, you always get it correct. If you stick to this, you may get some questions wrong. So that is why I'll do a full video on this so that you can answer any question on this. So this is our introduction. Thank you. Oh, sorry. So we were going clockwise, so it's going to be R. I'm not really doing the naming. I just want to know the configuration is R. If you have a problem with naming of organic compounds, you let me know, and we have class on that, or I do a video for you. So this is R. If it's clockwise, you give it R. If it's anti-clockwise, you give it S. That's when you ignore the number four and you try to trace one, two, and three. We are going one, two, three. Yeah, we are going clockwise. So it's R.